Newton's comprehension of gravity was enough to permit us to travel. But have you ever been to the moon, or even thought about the Earth differently? We are often thrown off balance by the endless time spent pondering whether our perception of reality is merely the tip of a massive temporal iceberg. His insight is much more than just a theory. It's a key that could unlock the mysteries of the cosmos, revealing a universe far more complex, amazing, and inspiring than our wildest dreams. Most recent theory by Brian Cox challenges our traditional conceptions of time. What kind of effects could this have on our understanding of the world? Join us on an exciting journey through the corridors of time as we delve into Brian Cox's recently revealed, groundbreaking theory about how time works in the universe around us. Many mysteries remain unsolved, and these challenges concern the fascinating aspects of time and gravity, two forces fundamental to our existence. We live in a reality where time moves in unpredictable ways. It can slow down or speed up. Moreover, the force that holds us down, the one we call gravity, may not be what it appears to be. This leads us into the domain of Albert Einstein's theories of relativity, in which our comprehension of time and gravity takes an unexpected turn. Albert Einstein, a celebrated figure, offered us a fresh perspective on the universe through his revolutionary relativity theories. These laid the foundation for how time functions under diverse circumstances, particularly when moving at extremely rapid speeds. The journey began at the turn of the 20th century, when Einstein proposed two groundbreaking theories: the special theory of relativity and the general theory of relativity. The special theory of relativity, first published in 1905, altered how we perceive time and space. In simple terms, it states that the laws of physics are consistent for all observers who are not accelerating. This theory presents the concept of relativistic effects, including the well-known notion that time can slow down under certain conditions. One intriguing thought experiment demonstrating this is the light clock. Imagine being inside a spacecraft traveling nearly at the speed of light. Within the spacecraft, a beam of light moves between two mirrors placed opposite each other, perpendicular to the direction of travel. According to physics, the speed of light is constant for all observers. Therefore, the light beam must appear to travel a longer, diagonal path to an outside observer. Since the speed is constant, it must take more time to complete its journey. This perceived difference in duration is what Einstein termed time dilation, the idea that time appears to move more slowly for the moving observer relative to a stationary one. Understanding how phenomena change at high speeds is central to relativistic effects. This is not merely a theoretical idea. Scientists make use of massive machines like particle accelerators, such as the Large Hadron Collider, to accelerate particles to speeds approaching that of light. At these extreme velocities, we must reconsider how we approach time, predictions, and measurements. Einstein's special theory of relativity revolutionized our understanding of the universe, especially concerning motion and time. The theory challenges our preconceived notions, proposing that there is a limit to how fast anything can travel, the speed of light. This constant results in unexpected conclusions, such as events that appear simultaneous to one observer may not be to another moving near the speed of light. Another concept emerging from this is length contraction. When an object is in motion, it appears shorter in the direction of movement when viewed from a stationary position. Then there is the famous equation E=mc2, which shows that energy and mass can transform into one another. This is essential for understanding the behavior of tiny particles moving at high speeds, and for phenomena like nuclear reactions, such as those in nuclear fission. In reality, special relativity is not merely an abstract theory. It plays a significant role in everyday technologies like GPS. When GPS satellites transmit signals, they are moving. Because of this, time behaves slightly differently for them. If we failed to account for time dilation in our GPS calculations, navigation systems would become significantly inaccurate. Therefore, special relativity teaches us that time is not constant for everything and everyone. It depends on the motion of the objects involved. This concept challenges our everyday comprehension of space and time, almost like saying our usual view of the cosmos may be slightly skewed. According to the special theory of relativity, time is not fixed. It is influenced by motion. Several fundamental concepts, like the speed of light remaining constant and the relationship between energy and mass, have been verified by numerous experiments. However, there is more. Enter the general theory of relativity, published by Einstein in 1915. This theory delves deeper into the relationship between gravity and the structure of the universe, shattering the outdated belief that gravity is simply a force pulling objects from a distance. Instead, it shows that gravity arises because space and time are curved or distorted. It's as if gravity is not an obscure force, but a natural outcome of the way objects interact with the fabric of space-time. Einstein's concept of relativity requires viewing the universe as a four-dimensional entity, combining three spatial dimensions with time. Within this framework, large bodies, such as planets and stars, have a direct effect on the curvature of space-time around them. What we perceive as the force of gravity is actually this curvature. Space-time can be imagined as a vast, flexible fabric. When a heavy object like Earth is placed on it, it causes a depression, bending the fabric and pulling smaller objects toward it. If you position something near Earth, something smaller than a ball, it will roll towards the depression, just as objects get closer due to what we perceive as gravitational forces. A concise explanation is provided by general relativity for the movement of celestial bodies in our solar system, like how the planets move around the sun. This also makes it possible for us to accurately predict the paths taken by planets, such as the elliptical orbit of Earth around the sun. According to Brian, this view differs from the stale notion that gravity simply brings objects together to form a concept, which struggles to explain planetary movement. The new perspective shows that time and space are curved, like flexible fabric, which provides a more precise explanation for the behaviors that were observed. A significant event in the universe that confirmed the validity of general relativity occurred during a solar eclipse in 1919. This was led by Sir Arthur Eddington, an expedition to observe how light from distant stars bent as it got closer to the sun. According to the theory, the mass of the sun ought to cause the light to curve slightly during the eclipse, and the observations aligned perfectly with Einstein's predictions, further cementing the accuracy of the theory. General relativity alters our experience of time. According to special relativity, gravity also alters the passage of time. In areas where gravity is incredibly strong, time moves more slowly compared to areas with weaker gravitational forces. If you were near a massive object like a black hole, your clock would tick slower than one placed far from this immense mass. General relativity introduces the concept of regions in black holes, where the gravitational forces are so overwhelming that nothing, not even light, can escape. The boundary surrounding a black hole is known as the event horizon, which marks the point of no return. Once something crosses this threshold, it is dragged into the black hole with no possibility of escaping. Einstein's theory of general relativity has profound implications for our understanding of the cosmos. Initially, Einstein incorporated a concept known as the cosmological constant in his equations, as he believed the universe was static. But when the universe's expansion was discovered, he later considered this a mistake. The idea of an expanding, general relativity-based universe is fundamental to the Big Bang theory, which explains the origin of the universe. Another important concept that arises from general relativity is gravitational waves, space-time ripples brought about by massive objects moving quickly, such as the collision of black holes or neutron stars. In 2015, researchers at the Laser Interferometer Gravitational Wave Observatory, LIGO, directly detected gravitational waves, providing further proof of Einstein's theory. Despite facing challenges from alternative theories, general relativity remains the most significant and successful structure for comprehending gravity. It consistently holds up in tests, from observations of planetary motion to the bending of light around massive bodies, as well as the discovery of gravitational waves. While questioning gravity might seem radical, especially since we experience it daily, it's common in science to explore and critique existing theories. Frequently, researchers like Brian Cox challenge established ideas in the realm of gravity. Some propose alternatives, such as modified Newtonian dynamics, MOND, which suggests gravity behaves differently at lower speeds, particularly in galaxies, without invoking dark matter. Instead of introducing unseen matter, MOND suggests that gravity strengthens at slower speeds. The discussion about gravity also encompasses the mysterious concepts of dark matter and dark energy, which were introduced to explain certain cosmic phenomena. Critics argue that these ideas might not be necessary, and that the same observations could be explained by alternative theories. Some scientists who disagree with Einstein's theory of gravity are looking into new possibilities, such as theories involving unknown particles or forces that could modify or improve our comprehension of gravity. It is important to note that in science, new thoughts are not completely discarded. They are put through numerous tests and evaluations for their veracity. Einstein's view of time, which involves four-dimensional space, where time travel might be limited by the speed of light, has sparked creative exploration of concepts like shortcuts and wormholes. Stephen Hawking's chronology protection hypothesis, for example, suggests that traveling back in time is likely impossible. Experiments and ongoing observations continue to test these new theories to see if they can explain phenomena like gravity in ways that conform to current knowledge. Despite many new ideas being proposed, none have yet successfully replaced the well-established laws of gravity. Challenging and pondering existing theories are necessary for scientific progress, leading to deeper insights and a broader understanding of the universe. In the case of gravitational theories, general relativity remains the most effective and widely accepted framework, even though it continues to face challenges posed by different theories.